In this video, we're going to talk about the chair conformation of cyclohexane, as well as how to draw a ring flip. But let's start with the bond line structure of cyclohexane. It looks like that. Now let's convert it into its chair conformation. So what we're going to do is we're going to draw two parallel lines, and then two more parallel lines with the same length, and then another two parallel lines. So that's a simple way of drawing the chair conformation of cyclohexane. Now this first carbon atom has two hydrogen atoms. The same is true on this carbon atom. It has two hydrogen atoms, but the way we show it is going to be a little different. There's two types of bonds that you need to be familiar with: the axial bond and the equatorial bond. The axial bond can go straight up or straight down. The equatorial bond kind of veers off to the side. So let's draw all the axial bonds. So if this is axial up, the next axial bond will be down, and it's going to alternate. This is going to be axial up, axial down, axial up, axial down. This equatorial bond is kind of slanted downward. The next one will be slanted upward, and then down, up, down, up. So that's how you could show all of the axial and equatorial bonds for the chair conformation of cyclohexane. Now let's work on an example problem. Draw the most stable chair conformation of methylcyclohexane. So first, let's draw the bond line structure. So this is cyclohexane, and we just have a methyl group. Now let's draw the chair conformation. So let's start with our two parallel lines, and then we'll draw two additional parallel lines and so forth. Now, we could put the methyl group in the axial position, or we could put the methyl group in the equatorial position. In both cases, this represents methylcyclohexane. But which one is more stable than the other? Is it better to put the methyl group in the axial position or in the equatorial position? Which configuration is the lower energy configuration? If we put it in the axial position, there's something known as 1,3 diaxial strain. This methyl group is going to interact with these hydrogens. If we call this carbon 1, it's going to interact with the hydrogen on carbon 3, regardless of where you count it from the methyl group. So because of this 1,3 diaxial interaction, the axial position is less stable than the equatorial position. So this is going to be the answer. The chair conformation will be more stable if we put the methyl group off to the side in the equatorial position, because we will avoid this 1,3 diaxial interaction. Now what about this example problem? Draw the most stable chair conformation of 1-tert-butyl 4-methylcyclohexane. So let's begin by drawing the chair conformation. So let's put the tert-butyl group on carbon 1. So that's our tert-butyl group. And let's put the methyl group on carbon 4. So this is one way in which we can draw 1-tert-butyl 4-methylcyclohexane. This is in the axial position, and this is in the axial position. So in terms of stabilities, there's four different types of stabilities that we can have here. It could be axial-axial, axial-equatorial, equatorial-axial, or equatorial-equatorial. So let's draw four different combinations based on what we just saw. So let's keep the tert-butyl group in the axial position, but now let's move the methyl group to the equatorial position. So if this is axial down, this is going to be equatorial up. And let's draw another one. So this time we're going to put the tert-butyl group in the equatorial position. And let's keep the methyl group in the axial position. And let's draw one more conformation. So this time, the tert-butyl group will still be in the equatorial position, and the same will be said of the methyl group. Now let's rank the stability of the four conformations that we see here. So we're going to say that number 1 is the most stable, number 4 is the least stable. So which one is going to be the most stable chair conformation out of what we have listed here? The most stable is going to be the one where both groups are in the equatorial position. So this is number 1. The least stable is going to be the one where both groups are in the axial position. So that's this particular conformation. Now between these two, which one is more stable? Will the stability increase if we put the tert-butyl group in the equatorial position or the methyl group in the equatorial position? Because in both cases, one is axial, one is equatorial. In order to determine which conformation will be more stable, you want to look for the one where the bulkiest group is off to the side. So we can reduce the potential energy of this molecule by putting the bulkiest group on the equatorial position. So this is going to be more stable than this one. So this is the most stable, this is the second most stable, that's the third, this one is the least stable. So the answer that we're looking for in this problem, we just want to draw the most stable chair conformation, and it's this one. It's the one where we put the most bulkiest groups in the equatorial position. Now consider this problem. Identify the following chair conformations as cis or trans isomers. So how can we do this for each of the conformations that we see here? All we need to do is identify if it's up or down. So looking at this methyl group, it's in the axial position, but it's up. For this one, it's axial, but it's facing downward. If one is going up and the other is going down, it's going to be trans. I'm going to put T for trans. Now looking at the next one, this is axial up, this is equatorial up. Because they're both facing upward, this is going to be cis. They're going in the same side. Now for the next one, this is equatorial down, this is axial down. They're both going in the downward direction, so the same direction. Thus is going to be cis. Next, this is equatorial down, axial down. Same direction, this will be the cis isomer. For this one, this is equatorial up, equatorial down. So if one is going up, the other is going down, this is going to be trans because they're going in opposite directions. And for the last one, this is axial down, equatorial down. So that's going to be the cis isomer. So that's how you could determine if a particular chair conformation is a cis isomer or a trans isomer. Now let's focus on ring flips. Let's talk about how we can draw a ring flip. So let's begin by drawing the chair conformation of cyclohexane. And let's say we have a methyl group on carbon 1. So let's number this. Let's say this is 1, 2, 3, 4, 5, 6. Now to draw the ring flip, instead of drawing these parallel lines slanted to the right, we're going to draw the mirror image. We're going to slant them towards the left. And then we're going to draw 2 parallel lines and then 2 short parallel lines. So let's call this form A and form B. Going from form A to form B, you want to move these numbers in the clockwise direction. So this carbon, which was carbon 1, was there. It's now going to be here. And each other number is going to move one position in the clockwise direction. Now the methyl group was in the axial position, and it was in the upward direction. Anytime you draw a ring flip, the groups in the axial position, they're going to go into the equatorial position and vice versa. So if the methyl group was in the equatorial position, it's going to go in the axial position. Now, if a group is in the up position, it's going to stay up. If it's in the down position, it's going to stay down. So when doing a ring flip, the only thing that changes is the axial and equatorial bonds. The way they're directed up or down, that part doesn't change. So the methyl group, it was in the axial position. Now it's going to be in the equatorial position. So this part changed from A to E. But it's not going down, it's still going up. So that's a quick and simple way of how you can draw a ring flip. Now just to recap, if you're going from form A to form B, just remember these numbers, you need to move them in the clockwise direction. And if you're going from, let's say, form B to form A, then these numbers, they get moved to or in the counterclockwise direction. So be mindful of which form you're starting from. Now these two forms of methylcyclohexane, these two chair conformations, they're interconvertible. One form can convert into the other form. So what type of arrows should we put here? Should we put arrows that are equal in size, or should one be significantly bigger than the other one? Which set of arrows should we use? Well, notice that these two chair conformations are not equally stable. Here the methyl is in the axial position, here it's in the equatorial position. And we know putting a methyl group in the equatorial position reduces the 1,3 diaxial interaction between the methyl group and the hydrogen atoms. So therefore, this structure is more stable. So because it's more stable, this particular reaction, the way it's written, it's going to be product favored. So we're going to use this set of arrows. So we're going to have a bigger arrow towards the right, a smaller arrow towards the left. So the two arrows help us to see that it's reversible. However, the position of equilibrium is towards the right. This particular reaction is product favored. The bigger arrow shows you which conformation is more stable. Let's work on this example problem. Perform a ring flip on the chair conformations shown below. So looking at the first example, let's call this carbon 1, 2, 3, 4, 5, and 6. Now, what form of the chair conformation do we have? Form A or form B? Notice that the lines are slanted to the right with a positive slope. So therefore, this is form A. To go to form B, we need to move the numbers in the clockwise direction. So first, let's draw two parallel lines with going down with a negative slope. And then let's draw two additional parallel lines and then connect them. So this bromine atom, well first let's move the numbers. So this was carbon 1, this is now going to be carbon 1. So this will be 2, 3, 4, 5, and 6. This bromine atom was in the axial position. Now it's going to be in the equatorial position. It was axial up, but now it's going to be equatorial up. Now this bromine atom is equatorial up, but on carbon 2 here, it's going to be axial up. So up remains up, but axial changed to equatorial and vice versa. So this is the ring flip of this structure. Well, that's the conformation that is produced when we flip this ring. Now, which structure is more stable? Notice that the stability of these two molecules is the same. This is in the axial position, that is in the equatorial position. So we have one axial, one equatorial, and the same is true here. We have an axial bromine and an equatorial bromine. So because they're equally stable, we can draw a reversible reaction with two arrows of the same length. So 50% will be in form A, the other 50% will be in form B. So they can easily interconvert from one form to the other. Now let's focus on the second example. Which form of the chair conformation do we have? Is it form A or form B? So notice the lines. The slope of those two lines are negative, so therefore we have form B. And we need to convert it to form A. So let's draw two parallel lines with a positive slope. And then everything else will follow. Now, in order to do the ring flip, because we have form B, we need to go to form A. This time, we're going to move the numbers in this direction. So this is carbon 1, 2, 3. So this is going to be carbon 1. This will be 2, and this is 3. So now the tert-butyl group was in carbon 1, and it was in the axial position in the upward direction. So axial is going to become equatorial, but it's still going to be in the upward direction. Now on carbon 3, we have a methyl group in the equatorial position going in the downward direction. So carbon 3, we're still going to have a methyl group, but it's going to change from equatorial to axial. But it's going to remain in the downward direction. So this is down, that's down. This is up, and that's up. So that's how we could perform the ring flip in that case. So we just need to move the numbers in the clockwise direction, going from B to A. But going from A to B, we would move the numbers in the clockwise direction. So wait, let me just in case I said that wrong, I'm just going to repeat that. So going from B to A, we need to move the numbers in the counterclockwise direction. But from A to B, we move it in the clockwise direction. So now that we've drawn the chair conformation that results from performing a ring flip on form B to get form A, now let's talk about stability. Which of these two structures, or two chair conformations, is more stable? Is it form B or form A? In each case, we have one group in the axial position, one group in the equatorial position, but we do have a bulky tert-butyl group, and we can greatly increase the stability of the whole chair conformation by putting the bulky tert-butyl group in the equatorial position. Therefore, the structure on the right will be more stable than the structure on the left. This structure is less stable. So the position of equilibrium is going to favor the product or the reactant that is more stable. So we're going to have a bigger arrow that points to the right and a smaller arrow that points towards the left. Now let's work on this example. Convert the following structures into their corresponding chair conformations. So for the first one, we have the trans isomer. Now let's draw a chair conformation that corresponds to it. So let's put the methyl group on the first carbon at the top. Now notice that the methyl group is on the wedge, which means it's coming out of the page. Therefore, we're going to put it in the up position. Now the bromine atom is on the dash line. It's on the hatch wedge. So it's going into the page. This is coming out of the page, that's going into the page. So for into the page, we're going to put the bromine atom going down. So if we were to number the carbons, this is carbon 1, 2, 3. 1, 2, 3. So on carbon 3, bromine has to be going down. It's not going to be axial up, but it has to be equatorial down. So that's one possible chair conformation that we can draw for this structure. It's not the only one. There are other ways you can draw it as well, but this is just one possibility. So for instance, let me give you an example of another possibility. So instead of putting the methyl group on the axial up position, what we could have done, we could put the methyl group in the equatorial up position. As long as it's in the up position, it's going to work because the methyl group is on the wedge. So anything that's on a wedge, you want to place it in the up position. If it's on a dash, place it in the down position. So now this will be carbon 1, this is going to be 2, and this is going to be 3. So this is going to be down, but it's going to be axial down. So these two structures, they both correspond to the trans isomer. As we can see, this is up and this is down, which makes it trans. So now draw one possible chair conformation that corresponds to that structure. So let's put the hydroxyl group on this carbon. So this is on the solid wedge. We want the OH group to be going up. So that's axial up. Now the chlorine atom is also on a solid wedge, which means that when we put it on the chair conformation, it needs to be going up. Now let's number this. So let's put OH on carbon 1. Where should we put the chlorine atom? Should this be carbon 2 or should this be carbon 2? In a situation like this, we need to make sure that we're counted in the same direction. So here we're counted in the clockwise direction. So we need to do the same thing. We need to count in the clockwise direction. Therefore, carbon 2 should be here. And this is going to be equatorial up. So that's it for that example. So that's one way in which we can draw the chair conformation for it. Now let's focus on this one. So we can make this carbon 1 or we can make that carbon 1. We're not trying to name it using IUPAC rules. We're just putting the numbers in so we can draw the correct chair conformation. So let's count this in the clockwise direction. And let's put the methyl group on carbon 1. So it's on a solid wedge, which means we need to put the methyl group in the up position. And if this is carbon 1, counting it in the clockwise direction, this is going to be carbon 4. So in carbon 3, the bromine is in the back. It's on the hatch wedge. So that means it needs to be facing down. So on carbon 3, we can either put it in the axial up position or the equatorial down position. So we need to put it in the equatorial down position. Now on carbon 4, the OH group is on the solid wedge. So we want it going up. So we got to put it in the equatorial up position. And so that's it for these problems. Now you know how to convert a bond line structure into the corresponding chair conformation.